Neutron stars begin their fun after their star, which has to be at least 8 times more massive than our sun, which I guess means no fun for us, collapses in on itself because it cannot fuse particles to push against its gravity. In this simulation, I'm using Betelgeuse. Betelgeuse is expected to go supernova, in other words, collapse on itself, relatively soon compared to other stars. Even compared to our sun, which isn't going to go supernova, but it's not going to die for a few billion years. Betelgeuse is special here because when it collapses in on itself, it could become a neutron star. Now, the core needs to be 1 to 3 solar masses, or 1 to 3 masses of the sun. If that is the case, the electrons and protons in the core collide and form neutrons. The newly created neutrons, along with the previous ones, can stop the collapse, leaving a very hot, very dense, possibly spinning multiple times a second object called a neutron star.
Alright, so this is a blender. And just to show you a little something, I'm going to turn this thing on, and I'll explain it afterwards. Put it all the way at 10. Pray for me. Loud! Now, as fast as that was rotating, the point is that a neutron star can spin faster than the blades on this thing. I mean, look at that, blades. Oh, blades, please, blades. Oh, where are the blades at? Let me open this thing up so you can better see the blades. See, blades. Now, these blades right here can spin very fast, very, very fast. A neutron star can spin as fast as these blades. That is crazy. That is absolutely crazy. I mean, you saw that level 10 right there. That was kind of scary, honestly, but it was very fast.
Alright, now that you have enough knowledge, let's start off with the first type, pulsars. Most of the observed neutron stars are pulsars, but don't let this come off as anything less than ferocious. Often called the lighthouses of the cosmos, jets of particles shoot from the magnetic poles. As the star rotates, the beams go all around, looking a lot like a lighthouse. In this case, we have PSR 21443933. This is a pulsar with the mass of 2 suns. It's only 13.1 kilometers in diameter, which is crazy small. And as you can tell here, it's very, very dense. Even if I bring it to, it's a kilogram, that's still, oh, oopsies, wrong thing. Oh wait, no, right thing. Where are we? Here. Even if I bring it down to a kilogram, quite a big number. Bringing down to this, quite big number. It's just gone down by half, but still.
The second type of neutron stars are magnetars, the extremes of the extreme. As we covered before, in a typical neutron star, the magnetic field is trillions of times stronger than the Earth's magnetic field, which keeps us alive. Magnetars have an even stronger magnetic field, 1,000 times stronger. Now, double would have been crazy, triple would have been crazy, heck, 10 times the strength would have been absolutely mind-blowing. But 1,000 times stronger? That's unbelievable. For magnetars, the sensitivity and power are turned up. The slightest change in the crust or magnetic field means an enormous eruption. This eruption is usually of high energy light. On December 27, 2004, satellites and telescopes observed an eruption like the one we are talking about from a star named SGR 1806-20. This star released in 1/10 of a second more energy than the sun has emitted in the last 100,000 years. Yes, neutron stars are absolute monsters, but I think that is sick. And so do the people studying these things. Neutron stars are a stellar example of what happens in special conditions and are one of the only ones that we can directly observe. There's still so much to learn and say about these beasts. I can't wait to learn more about them and let you know. To stay in the circle, you should subscribe and like. Adios.